Saket Kumar Singh and I am working as an assistant professor in Department of Computer Science Engineering, Ajay Kumar Garg Engineering College, Ghaziabad. So in this lecture we are going to see some brief details about how what are the different input output devices, how do an operating system manages these input output devices. There are n number of input output devices and how this operating system manages all those input output devices, and we will see some of the IO subsystems and IO buffering, IO kernel IO structures, okay, in this lecture. Okay, so now the outline for this lecture will be: first we will see input output hardware, then we will see application IO interface, okay, and then we will see some kernel input output subsystems which includes your spooling, buffering, caching and all, and then we will see improving performance, that how we can improve the performance of a input output subsystems. Okay, so let's start with the IO hardware. So what are the hardwares, what are those hardwares inside this input output? So it is an incredible variety of input output that resides inside this input output. So the control of devices, okay, so the control of devices connected to the computer is a major concern of operating system designers. Okay, whenever an operating system is designed by some programmers, okay, the main thing is control of devices connected to the computer. What are those things that are connected to the computer? A keyboard, a mouse, a monitor, each and every input output devices is a major. So to control all these connections, to control all the attachments of the computer, this is a major challenge for the operating system designer, because input output devices vary so widely in their functions and speed. Each and every device is having their different speeds. Okay, so like consider a mouse, a hard disk and CD-ROM, jukebox, etc. Varied methods are needed to control them. They cannot be controlled by a single way or a single structure, because each and every devices are having their own different properties, they are having their own different attribute, they are having their different speed, okay, they are having their different each and every input output devices have their own speed and properties. Okay, these methods from the IO subsystem, these methods forms the IO subsystems. Okay, input output subsystems, like how we are going to control different input output devices. This is what is called as input output subsystems of the kernel. You have already seen kernel in your lecture number 5, which separates the rest of the kernel from the complexities of managing input output device. So you know that kernel is very much important. You know that kernel is the central part of operating system, responsible for providing us the interface, providing a user an interface to work on. It provides the platform for a programmer to execute their programs. Okay, so kernel is very much important. So just think that we will use the whole kernel in managing this input output devices will be difficult. So we are just separating the work of kernel and IO input output management. So computers operate an incredible variety of devices, and most fit into the general categories of storage devices like disks, tapes, transmission devices like network cards, modems, and human interface devices like screen, keyboard and mouse. Okay, so we must understand how devices are attached and how the software controls the devices. A device communicates with a computer system by sending. So this is the whole way. In this slide we are going to see what is happening in the background. So a device communicate with a computer system by sending signals over a cable or even through the air also, air as a medium. The device communicates with the machine via connection point, or this is also called as port, for example a serial port. Okay, So if devices uses a common set of wires, the connection is called as bus or the system bus, that we will see the diagram. In the diagram, a bus is a set of wires and a rigidly defined protocol. Protocol means set of rules and that specifies a set of messages that can be sent on the wire. So this protocol generally specifies a set of messages that can be sent on the wire. A bus is a set of wires. Bus is not a single wire. In terms of electronics, the messages are conveyed by patterns of electrical voltage like +5, -5, or whatever the encoding technique is being used. So these patterns of electrical voltage, the messages are conveyed by patterns of electrical voltages applied to the wires with the defined timings, okay. So now when device A has a cable that plugs into device B, for example, and device B has a cable that plugs into device C, and device C plugs into a port on the computer, this arrangement is called as daisy chaining method, okay. So this is called as daisy chain method. So what is daisy chain? Daisy chain is nothing but it's just an arrangement that how the wires are arranged. Okay, a daisy chain usually operates as a bus. The next level is your controller. A controller is a collection of electronics that can operate a port, a bus, or any other device. Okay, so anything that needs to be operated must have their, any hardware that needs to be maintained or managed must have their own controller. Okay, a serial port is also a controller. It is a single chip or a portion of a chip in the computer that controls the signals on the wires of the serial port. So now the question arises that how can the processor give commands and data to a controller to accomplish an IO transfer? How can a processor means CPU, give commands and data to the controller, this controller, to accomplish an IO transfer? Okay, so two ways are: the controller has one or more registers for data and control signals. Controller is having one or more registers for data and control signals. The another is the processor communicates with the controller by reading and writing bit patterns in these registers. So these are the two ways to answer those questions. One way in which this communication can occur is through the use of a special IO instructions that specify the transfer. Special IO instructions that specify the transfer of a byte or word to an input output port address. The input output instructions trigger bus lines to select the proper devices and to move bits into or out of the device register. Alternatively, the device controller can support memory mapped IO. Okay, memory mapped IO. In this case, the device in memory mapped IO, the device control registers are mapped into the address space of the processor itself. Okay, but I hope you all have already studied this computer system organization and architecture. So this is the prerequisite for understanding this lecture. The CPU executes IO request using the standard data transfer instructions to read and write the device control registers. Some systems use both the techniques. For one is your memory mapped and another is your programmed IO. For instance, interrupt or memory mapped or instructions IO. So some systems use both the techniques. For instance, PC use IO instructions to control some devices and memory mapped IO to control others. So some systems use both the things. First is your IO instructions and another is your memory mapped. So we'll see later on what is programmed IO and DMA and interrupts. An IO port typically consists of 4 registers. So let's see the responsibilities of those 4 registers. First is your data in register, which is responsible for reading by the host to get the input. data in register contains the content that is to be read by the host to get the input from the keyboard or anywhere. Data out register is written by the host to send output. Data out register, who handles this data out register? By the host. The host could be the controller or the driver or even the CPU. Okay, so is written by the host to send the output. So whomsoever is using that will behave like a host. So a status register. Now the third one is the status register that contains bits that can be read by the host. Okay, so these all will be clear when we'll see the concept of polling. Okay, these bits indicates states such as whether the current command has completed, whether a byte is available to be read from the data in register, and whether a device error has occurred. Okay, so a control register is the fourth one, which can be written by the host to start a command or to change the mode of a device. For instance, a certain bit in the control register of a serial port chooses between full duplex and half duplex communication. Another bit enables parity checking. Third bit sets the word length to 7 or 8 bits, and another bit select one of the speed supported by the serial port. So this is a simple typical bus structure. Here you can see this is your processor. In between this processor and memory there is a cache, and there is a memory controller. Whenever you are talking about some hardware, it should have its own controller. So this is, you can see this is your memory, and there is a memory controller. All are connected to this PCI bus. Okay, even you can see the monitor is having graphics controller, processor is having memory and bridge controller, ID, these discs are having this ID disk controllers, bus, even you can see parallel port, serial ports, keyboard, all these are connected to an expansion bus, and these some of the small discs are connected to this SCSI, small computer system interface bus. So this was the structure. Now we will understand three types of techniques used for IO transfer. First is your polling. It determines states of devices from the status register that we have already seen, the 4 registers. So state of a device from polling gets the state of the device from the status register. It uses command ready bit, which is set by host. Command ready bit, like suppose if the host is ready, so host will set command ready bit to 1. Okay, now busy bit, like if the controller is busy somewhere, or if the controller is free now, but if the controller is free now but it wants it is taking the responsibility of this command ready, so it is taking some task. Okay, now it will set the bit to 1, means now it is busy. Okay, similarly error bit is used by the controller clears the error bit when IO is successfully done. This error and busy bit is set by the controller. Okay, busy wait cycle to wait for input output from the devices. So this is very simple. The host will set the command ready bit whenever it is whenever the host is ready to execute, and that will depend on the controller whether the controller is busy or not. This we do in pooling. Next method is to use the interrupts. So CPU interrupt request line triggered by the input output device. So there are several interrupt request lines which is triggered by input output device whenever an input output device wants to have a communication. Okay, so interrupt handlers receives interrupts. So let's see the diagram directly. We'll come back to this DMA later on. So this is a diagram. Here you can see CPU is continuously sensing the what is the what a CPU is continuously sensing. You can see it is sensing the interrupt request line. Okay, so if any time and any IO is initiated, it will sense, it will be loaded into the interrupt instruction line. whenever it initiates input ready, output complete, or error generates interrupt signal. So any of these possibility will happen, there interrupt will be generated. Now this is your step 4. When CPU receiving interrupt transfer, the CPU will leave the control and it transfers the control to the interrupt handler. Now interrupt handler processes data and returns from the interrupt handler will then process the data and returns from interrupt. Now CPU will resume processing of the interrupted task. So whenever an input output device wants to communicate, it just load into the instruction line. Okay, now come back to this DMA. So whenever in here you can see this is important, interrupt request line. So whenever input output wants to communicate or wants to send some like keyboard wants to send some or output, CPU wants to print some output on the monitor, it will just update this interrupt request line, and this interrupt will be handled by the interrupt handlers that we have already seen in our. I have already told you that we will see interrupt handler when we will see the input output hardware. Now the next method is direct memory access. So direct memory access is used to avoid programmed I/O. So some operating system supports programmed I/O. They just fix some general purpose, specific purpose registers to handle the input output, but the use of programmed I/O is not beneficial when you are talking about large data movement. Large data movement involves disk movement, disk transfers. Okay, so any file that you are moving from disk 1 to disk 2 is a large data movement, and these two methods along with this programmed I/O would not be beneficial when you are talking about this large data movements. So this requires a direct memory access, which requires DMA controller. It bypasses CPU to transfer data directly between I/O devices and memory. So let's see figure number 3. So here you can see this is your step 1. Device driver is told to transfer disk data to buffer at address X. Okay. Now device driver tells disk controller to transfer C bytes from disk to buffer at address X. So this is your DMA interrupt controller, this is your DMA controller. Okay, and CPU cache, CPU memory bus. Okay, so you can see the communication is happening directly through DMA controller and memory. No intervention of CPU is there. Disk controller initiates DMA transfer, step 3, and then step 4 disk controller sends each byte to DMA controller. Disk controller sends each byte to the DMA controller. DMA controller transfers bytes to buffer X. So DMA controller will transfer the bytes into buffer X, increasing memory address and decreasing the C until C is equal to 0. Okay. So when C is equal to 0, DMA interrupts CPU to signal transfer completion. So now let's see about some of the application I/O interfaces. So what are these? This provides various structuring techniques and interfaces for the operating system that enable I/O devices to be treated in the standard uniform way. So this will also be more clearer when we'll see this figure number 4, but let's see some of the points here. Device driver layer hides differences among input output controllers from kernel. Okay, so device driver hides differences among input output controllers from kernel. So this device driver is responsible for hiding the differences among input output controller. Input output controller varies, like controller of a keyboard is different, controller of a mouse is different. Okay, so devices vary in many dimensions. Let's see how. First is your character stream or block. A character stream device transfer bytes one by one, whereas a block device transfers a block of bytes as a unit. Okay. Sequential or random access. Sequential device transfers data in the fixed order determined by the device, whereas the user of a random access device can instruct the device to seek to any of the available data storage locations. Other points are synchronous and asynchronous. A synchronous device performs data transfers with predictable response times. An asynchronous device exhibits irregular or unpredictable response times. Shareable and dedicated. A shareable device can be used concurrently by several processes or threads. A dedicated device cannot. So, a shareable device can be used concurrently by several processes or threads, but a dedicated device cannot, like we have seen L3 cache memory was shared while L1 cache memory was dedicated to different cores when we are talking about multi-core architecture. Speed of operation. Device speeds range from a few bytes per second to few GB per second. Read write, read only or write only. Some devices performs both input and output, but others support only one data direction. So, this is in a diagram. You can see this is your software and this is your hardware part. So, each hardware you can see keyboard is having its own controller, SCSI devices are having their own controller, mouse device is having their own controller, PCI bus is having own controller, but this device driver is inside the part of this software. Or this, how this software is divided: first is your kernel, then kernel IO subsystems, and then these drivers are here, which are hiding, which are providing an abstraction to us or the users. So, now we will see different kernel IO subsystems. So, let us see first is your scheduling. Some IO request ordering via per device queue, some OS try fairness. Okay. Next is your buffering. What is buffering? Store data in memory while transferring between devices. Store data. So, whenever you uses this YouTube or something and your net capacity is not that much, so that what happens then? Buffering happens. Buffering means the circle on the YouTube screen is rounding. Because why? Because to cope with device speed mismatch. Okay, because the device is playing the video very fast, but the network is slow. That's why the data is not streaming from the internet. So, here the case is vice versa also, to cope with the device speed mismatch, because device might be slow. Okay, and to cope with devices that have different data transfer sizes, and to maintain the copy semantics, so these three things, these are the scenarios, and that's why we use this concept of buffering. Okay. Next is your caching. We have already seen cache memory management in detail, but here it is different to cache memory, because here it is telling us the concept of how a caching can be helpful. So, it is fast memory holding copy of data. Fast memory holding copy of data, always just a copy. This is a key to performance. The difference between, we must understand the difference between caching and buffering. Difference between a buffer and a cache is that a buffer may hold the only existing copy. A buffer may hold the only existing copy of a data item, whereas a cache by definition just holds a copy on faster storage of an item that resides elsewhere. Okay. So, buffer is holding only the existing copy of a data item, but cache is holding the copy of data which is residing somewhere else. Okay. So, next is your spooling, which holds the output for a device. The best example is the printer. If a printer is shared to n number of systems, so printer can give the output one at a time, but multiple user systems can load the n number of requests to a printer. So, to handle these situations, spooling is used, which holds the output for a device if device can serve only one request at a time, like printing. Next is your device reservation. It provides exclusive access to a device. System calls for allocation and deallocation is required when you are using this device reservation. A few operating systems support this device reservation. Watch out for the deadlock. Otherwise, when you are reserving some resources, here you are reserving some device, so that means you are implementing hold and wait. Okay, so now let's see the two more things, that is your error handling and IO protection. So kernel IO system OS can recover from disk read, device unavailable, transient write failures, must return an error number or code when IO request fails. So whenever you are dealing with input output devices, there must be an error handling technique which return an error number or code when IO request fails. System error logs hold problems, problem reports. Next is your IO protection. There must be a protection. User process may accidentally or purposefully attempt to disrupt normal operations via illegal input output instructions. So all input output instructions defined to be privileged. These are some of the ways to provide protection to an input output request. So all input output instructions defined to be privileged. All IO must be performed via system calls. Even memory mapped and IO port memory locations must be protected too. So now in last I am going to discuss that how we can increase the performance, how we can improve the performance of a input output. So here you can see we must reduce the number of context switches, reduce data copying, reduce interrupts by using large transfers, smart controllers or polling, use DMA in place of polling and interrupts, balance CPU, memory, bus and IO performance for highest throughput. Okay, so that's all for this lecture. I hope you would like you would have liked different chapters that was taught by me or by Akhilesh sir. So thank you everyone. You may contact me whenever you find any doubt. Okay, thank you.